Why are you smiling?
Because, yeah, there's magic that went on
Oh,
there.
math magic, yeah. Yeah, I notice when math magic occurs.
I appreciate you calling it out. That made me.
Because that's the whole thing with identities. You have the answer, like when you start. So it's how do they equal each other? But the good news is that everyone survived. I was like, and we're basically back to numbers. I was like, we have a chapter 7 quiz, and then we have a chapter 9 take home, and the chapter 8 quiz basically serves as our final exam, right? In case you haven't looked ahead. So there's basically 3 quizzes, and 7 is pretty small, and then 8 is relatively substantial, and 9 is absolutely teeny. All right, but that's just a take home. There's not even a home fund for it. All right, we're back to numbers. All right, so for those who are going full real world, all right, but it is a trade-off. With back to numbers, it means you make sure you use your logic in conjunction, all right, when we solve these problems. And this actually is a perfect example of that. So I have a triangle here. And so I have A, C, and beta. And so our big thing is always to draw the picture. So there's A, B, and C is 4. And beta is our angle between them. And it doesn't matter where you start counting, right? Pick a side and that's your A and go from there. So this is a SAS triangle. And like I said, this is basically the most common triangle because knowing 2 sides and the angle between them, you're standing at a point. You can measure that side, you can measure that side, and you know the angle between them. So it's by far the most realistic example as well. In order to do that, we need to start with law of cosines. And we need to do the adjusted one. So draw your picture, right? We did law of cosines, we found our missing side. And then what is our other law? We only have two.
Law of sine.
Law of sines, and they're both sine, cosine, right? They're both named perfectly. Okay, so this is what I was gonna talk about. So start out, note, this is gonna be wrong. So sine of 45 degrees all over 2.95. And then basically we get to pick, right? So we have to use 45 and the angle and the side across from that angle. And then it seems like, okay, pick 2 or pick 4, right? And do the sine of the other missing angle. If I picked sine gamma and the 4 side, and again, I would solve this down and your calculator would not find any mistakes. I would get gamma equals 73.5 degrees, all perfectly fine calculation wise. And then, all right, in order to find that last angle, alpha, that would just be 180 minus 73.5 minus 45, which would give me 61.5 degrees. So back to our triangle, when I would put all these in, this is what I would get. And at first glance, looks fine, okay? If I'm not paying attention. What is the problem here?
61 isn't facing its proper side.
Right, so should I just flip them?
The 45 and the 61 should be flipped.
Oh, so I just flip those, no problem? The math here is the problem of the fact that it's 180. And a lot of times it's really just because your calculator is probably giving me the 180 degree off angle there. This happens, all right, because our calculator usually gives like 0, it always gives acute angles, right? It gives 0 to 90, things like that. And it's like a funny thing with the math. But absolutely, all right, the small side, here the problem is, the small side and small angle do not correspond. So I know this didn't work because the smallest angle and the small side have to be matched up, maybe medium and big. And this is just a matter of sometimes it's bad luck. And I always end up picking this one the incorrect way. If we redo that, and I have to start with sine 45 all over 2.95. But now I'm going to pick sine of alpha over 2. So exact same thing, but I picked the other angle. When we solve this down, alpha equals 28.65 degrees. And along the same lines, gamma equals 180 minus 45 minus 28.65. That would give me 106.35 degrees. And when I plug those values back in, so now back to our triangle. So the alpha side is this one, which we got 28.65 degrees. And this one was 106.35. How did we do now? And this lines up. All right, small, medium, big. And there is no way to prevent this, okay? Because the math works every time, and it's the only thing I see is that, so we had two options here, all right? The big and the small, and if you pick the small, that should work, but that's not a guarantee either, all right? So just be careful and verify at the end, all right? Making a picture, that's what we're all about. We have legit numbers with legit distances and everything, all right? And this one isn't in context, but we're gonna have a lot of context when we go through these problems. So make sure everything matches up. And that's always what we want. We want the logic. The calculation here, not difficult, very simple, very straightforward. Just make sure your logic lines up. Okay. I want to find the area of the shaded region of a circle whose radius is 8 feet formed by a central angle of 70 degrees. So we have to recall our equation for the area of a sector of a circle. All right, this was one of the first things we covered way back when. And that equation is A equals 1/2 r squared theta. And then once again, note theta is in rads. All right, all those formulas that we have, all these beautiful, nice formulas, they're almost always in radians, right? S equals r theta, V equals r omega, everything is always in radians. So we got to make sure we understand when you have a formula, how that angle is measured. You can't just put degrees in there and it'll still work out. As a note, the area of a sector of a circle, this should look relatively familiar because what's the area of a circle? Do you remember the joke we talked about?
Pi r squared.
Pi r squared. So the area of a sector, all right, so what's a full circle? What angle would that be? What degree if I go all the way around? What is it?
Oh. 2 pi.
2 pi. So if I put 2 pi in here, 2 pi times 1/2 is pi, and oh look, pi r squared. Okay, so that equation of course works. Okay, all right, so let's see. All right, back to what we're doing. Area of the shaded region. So I need the area of the sector and radius 8 feet and 70 degrees. All right, so for my theta, so let's start because in order to find the area of the shaded region, I basically need the area of the triangle and the area of the sector of the circle. And what do I do with those two values?
Plug it in.
What?
Plug it in.
I mean, I'll have two numbers. And I'll have the area of the sector of the circle and the area of the triangle. In order to find the shaded region, what do I do with those two values? What mathematical operation do I perform?
Right.
Subtract. Yeah, it's literally just subtraction. All right. I'm just trying to refresh us on our area geometry, right? All right, because that's all this is, right? I'm going to find this piece minus that piece, which gives me that piece. I mean, that's all we're finding. I just want to make sure we remember our area geometry. Okay, so let's start with the area of the sector circle, 1/2 r squared theta. And we have almost everything there, 1/2 8 squared, and theta, which is 70 degrees, I need to convert to radians, and 180 degrees equals pi rads. So 7/18 pi rads. And then I can actually put that in my equation. And feet. Since we're doing area of feet squared. We're we're back to the point where approximate is good, right? Don't you be exact whenever you can, but since we're back to once you're in degrees, it's pretty hard to be exact constantly with degrees. So a lot of times we're actually just going to write the approximated value. And then the other thing, this is an SAS triangle. And we actually have the equation of that. A equals 1/2 AB sine of the angle between them. And this can be in degrees or radians. It will come out correctly either way, but we're going to use degrees because it's just easier. I guess we do need the angle between here is clearly 70 degrees. This side is 8 and that side is 8, right? So actually, when you're dealing with circles, I was like, the two sides always end up being an isosceles. And calculate away there. And so the shaded area equals 39.01 minus 30.07. Oh, sorry, I wrote this down wrong. It's 30.10. And again, easy peasy. We are going to be heavy formulaic. So I like all the identities and all that because I feel like most of that I can keep in my head. I was like, we have a lot of little equations now, right? And being able to make sure you apply the correct equation. Also, we're basically off of our generic trig cheat sheet, right? All right. Let's look at some more in-depth applications. So the distance from the sun to the earth is approximately 149 million kilometers. The distance from the sun to Mercury is approximately 57 million kilometers. The elongation angle alpha is the angle formed between line of sight between the earth, all right, and Mercury. See the figure below. And we identify the elongation angle for Mercury is 15 degrees. Use this to find the possible distances between the Earth and Mercury. And at this particular angle, at any point, right, since it orbits in a circle, it's really no hole, all right? But since it orbits in an approximate circle, there are 2 points, which actually means that we have lots of triangles here to create. So we have the triangle of Mercury, Mercury, Sun, all right? We have the Earth, Sun, far Mercury, and the Earth, Sun, close Mercury. We are told, all right, this distance, all right, from the Earth to the Sun, all right, is 150-ish million kilometers. And we have Mercury to Sun is 58 million-ish kilometers. Now, we could start almost anywhere we want, but we really need to incorporate that angle. So that really gives us 2 big options. So that gives us the Earth, the Sun, and far Mercury, and the Earth, the Sun, and close Mercury. And to keep We're told that angle is 15 degrees, and this is 150 million. This one is 58 million-ish. This becomes our two triangles. Now, here's the weird thing. Okay? With this, I have two different looking triangles. Is any of the info different on them? No. Which means, are both these triangles going to be valid?
Wait, question.
Oh, go ahead.
Oh, is this the 150 and 58 the kilometers?
Yeah. This is 150 million, 58 million. We're approximating because I want to show this idea. We'll use the actual numbers when we, like, yeah, whatever, because whatever it is. I was like, because these are all actual distances and everything. All right, when you get actual distances, the numbers get ugly. All right, 57,910,000 kilometers, right? Ugh. Okay. But we need to identify this first. So with two different, okay, and if something is fixed, the point is these both can't be valid, okay? When you do this calculation, we'll actually realize that this one doesn't work. So to save us the time of going through, all right, of that just example we just did, when you would go through this, you'd realize the angles don't work, all right? And we have to use the Earth, Sun, Far, Mercury. Okay, so for the Earth, Sun, Far, Mercury. All right, now let's put the full numbers in. Okay. So with two sides and an angle, should I use law of sines or law of cosines? And the good news is there is only two, right? So even if you guess wrong, you start filling in stuff and realize it didn't work.
Sine.
Law of sines, right? And the biggest thing about law of sines is notice angle and the side that corresponds to it. Once you have that, that is the definition of law of sines. So sine of 15 degrees all over 5, 7, 9, 1, 0, 0, 0, 0. All right, and I'm gonna call this one beta. Sine of beta all over. Wonderful number here. That'll give us our angle beta. Similarly, then, I can find gamma. And then law of sines one more time. So. Okay, so plugging it back in, always double check, no matter how bad the numbers may be. All right, so 150 million corresponds to 42 degrees, 58 million, 15 degrees, 123 degrees to 188 million. So does everything match up? Yeah, okay, good. And when I solved C down here, all right, because we're dealing with the numbers, I didn't worry about what important thing do we have here? Units. Absolutely. We are fully in context, units, units, units. And actually, as a note, all right, by doing this, we already found one of the pieces of information. So we were looking, all right, remember what we were looking for, the possible distances between the Earth and Mercury. So we had two triangles that seemed like, oh, well, I can use these two triangles and I can find them both. That's what I was doing here. Because technically, the distance between the Earth's sun and close Mercury and the Earth's sun and far Mercury, oh, I have these same triangles. So when Mercury is far, it was 188 million kilometers. But if I do this all again, I will get when Mercury is close, it's still 188 million kilometers. Does that make sense?
Because all the numbers are the same, right?
All the numbers would be the same, but does that make close logically?
No.
Right, no, yeah, it would work out, but the concept isn't correct. So in order to find, all right, this triangle, I found the far, and now we need to take advantage of our small triangle here with far Mercury, close Mercury, and the sun. And then I could subtract that from my distance of Earth to the far Mercury to find the distance between Earth and the close Mercury. All right, so close Mercury, far Mercury, and the sun. Okay, so we have those. Those are nice. Do we know anything else? I was like, I have two sides. Kind of need more info. Oh, very good, right? Going back to this one, I have the sun and far Mercury, all right, and the Earth. Now, don't forget, that split right here to be close Mercury, which means that angle is still the same. So we had to find that our big triangle first in order to get the info for the small triangle. So I also know 41.96 degrees. And now I have all the info I need. And is this law of sines or law of cosines? Law of sines again, right? I have an angle and the side across from that angle.
So wouldn't the angle for close Mercury be the same since they're the same numbers?
You're a step ahead of me.
Okay.
This is actually a very particular kind of triangle. What kind of triangle is this? It's an isosceles triangle. Isosceles triangles, let's refresh. What's the definition of an isosceles triangle?
Two of the same sides.
Two of the same sides. What we don't focus on nearly as much, if you have two of the same sides, you have two of the same what as well? Angles. All right, so you have the same sides and the angle across from them has to be proportional. All right, and so hence, yes, you're absolutely correct. Okay, so I was going to solve. And so even if you didn't recognize that though, we could have solved it down and found that. And then we have, in order to find our last one, gamma equals 180 minus 41.96 minus 41.96. So our missing angle is then 96.08 degrees. And law of sines one more time. Means that missing distance is 86 million-ish miles. And then in order to find the distance between Earth and close Mercury, then we need to do our 88 million minus 86 million. And again, I was like, very nice. I was like, the numbers are a little yuck, but I was like, whenever you start getting into real world numbers, the numbers always become a little uglier. They're not as beautiful as pi over 3. All right. But it is good stuff. I was like, finding the relationships, looking at the picture. And again, what I definitely want to emphasize are things like this. This is where the logic definitely comes in. The rest of it is really a matter of following calculations. But you cannot have two triangles, all right, finding different distances, all right, with all the same info. And so you got to make sure that you logic that out. Yeah. A cruise ship maintains an average speed of 15 knots, right? And for those unfamiliar, knots are nautical miles per hour. That's all a knot is. Going from San Juan, Puerto Rico to Barbados, a distance of 600 nautical miles. To avoid tropical storm, the captain heads out of San Juan in a direction of 20 degrees off a direct heading of Barbados. The captain maintains 15 knot speed for 10 hours, after which time the path to Barbados becomes clear of storms. Through what angle should the captain turn to head directly to Barbados? Then we have another question. All right, so our picture, and sometimes it's given to us. All right, so San Juan to Barbados is 600 miles. He goes 20 degrees off of that. And then, all right, he's going 15 knots, all right, for 10 hours. So we need a distance. And then how do we find that? So this is what I was talking about with knots. So a knot, all right, I know it seems confusing, but a knot is simply just nautical miles per hour. So speed rate equals 15, basically miles per hour. And if you do that for time equals 10 hours, what's the calculation? for the distance. Yeah, it's D equals RT. Right? It's just 15 times 10. And so some of that is about just introducing what a nautical mile is. What nautical miles take into account what? Does anyone know?
Water resistance.
Nope. Curvature of the earth. Once again, I was like, so it's actually a more appropriate measure. All right, so that gives us 150 nautical miles, but again, we're gonna be lazy and just say miles. All right, so 150 miles, which gives us then this distance over here. All right. And again, see, we learned stuff. Just want to make sure, right? There's lots of different contexts, and I want to make sure that we're keeping up on so many different contexts that are out there. Once we're back in the real world, we can do all these things. It is interesting. So I have a side angle, side triangle. Again, one of our most popular triangles that we will see. Which means in order to find, I'm looking for this angle here, right? That's actually indicated. But in order to find that one, what do I need to find first? I need to find this guy, right? I need to find this guy, and then it will just be 180 degrees off of it. So this is law of cosine. Side angle side is the law of cosines all the way. And so that gave us the other missing side, because I need that in order to find. I need that. All right, so I need this side in order to then do law of sines. So now we can do sine of 20 degrees all over 461.9. Okay, and here's another thing we got to pay attention to in our calculation. Like I said, your calculator, when I do this in my calculator, when I do this calculation, right? Sine of 20 divided by 461.9 times 600, inverse sine, right? We can do this in our calculator, easy peasy. It spits out 26.4. So if I put 26.4 here, and we don't even have to calculate, but we could just estimate. So let's see, 180 minus, it's about 50. That's 130 degrees. Does this one make sense?
No.
No. So I could trade it. Or the other thing is that knowing what I'm looking at here, this has to be the biggest side. This, all right, is this 26 degrees or is that one 26 degrees? It's giving me the supplemental angle. And that's what I was talking about in that problem where I showed the wrong. So I could go through and I could double check the calculation and switch the law of sines too. But this one, I know that this is actually 180 off. My beta angle And it's pretty much always that problem. That's what I was talking about before. That your calculator is always giving you the acute angle when it should be an obtuse angle. It just doesn't, it always spits out angles less than 90. Which means, okay, so if we try this again, oops. That would be 153.6. And then this missing angle would then be and that one's actually 6.4 degrees. That's all that's left. So that one, okay, so now let's double check, all right? Big to big, small to small, all right, medium to medium. And it's those little tricks that are the hardest to actually make sure we're identifying. But it all comes down to double check it. And probably if we redid the law of sines and switched it up, so we did it for 600. If you switch it up and do it for 150, it would work out as well. Okay, so that's all about checking the logic. And my point is there's two ways to go about that. All right, you can identify, do 180 off of, or you can just stop and do the other law of sines, whichever one you prefer. Okay, so hence we would turn 26.4 degrees toward Barbados. Okay, once the turn is made, how long will it be? How long will it be before the ship reaches Barbados if the same 15 knot speed is maintained? And basically, given all our info, how do we find that one? So again, knot is just 15 miles per hour.
We divide 461.9 by 15.
Again, it's D equals RT. All right, and so I just want to make sure we're still using all that knowledge. That's not a trig thing. All right, but something like D equals RT, distance equals rate times time. I mean, that's not going away ever. All right, and you are absolutely correct. 461.9 equals 15, and we're looking for time. So again, just emphasizing the calculate away, and we would end up with 30.8 hours. It's just lots of little problems we can ask, right? Once we're in context, right? Are we doing okay? This isn't nearly as good as identities, but I mean, it's okay. I know, Macy, you're sad. It's okay. What?
So sad.
So sad. All right. Also, this gives us a chance to refresh on some other area notation and things that we'll see. So I want to find the area of the shaded region. Again, common thing. Enclosed in the semicircle of diameter 10 inches. The length of the chord PQ, all right, is 8, which is indicated on our picture here. Chord, again, that is just notation, a synonym for line segment, all right, in case you have forgotten. Because we don't call this a line because a line goes forever, right, in both directions. So a chord is a fancy way of saying line segment. And triangle PQR is a right triangle, okay, so that actually, that gives us that. Once I have that, then I can start identifying information and see what we need to find. One big thing, okay, so if that's 8 and that's 10, does anyone know what that missing side is? How'd you do that so fast? What kind of triangle is this?
remember the names of all the triangles.
This one doesn't have a full name. It's called a 3, 4, 5 triangle. Right? The most famous right triangle that exists, a 3, 4, 5. It just happens to be 6, 8, 10, right? Remember all multiples of this work as well. Or did you just do Pythagorean super fast in your head?
No, I did the 3, 4, 5. I did.
Okay. Okay, so yeah, so you did 3, 4, 5, you just forgot what it's called, yeah.
Yeah.
Yeah, and so this missing side is then 6, okay. And then in order to find the area of a triangle, and actually the area of this one. Okay, I actually wanted to do Huron's formula, but I just realized something else. So just to refresh what Huron's formula was, because this is a really commonly used one. So 6, 8, and 10 are my sides, but I could actually do this way faster. I was like, oh, I want to calculate Hurons, but actually don't forget what the A equals 1/2 base times height. I actually have the base and the height here. And this only works because this is a right triangle. If this wasn't a right triangle, this wouldn't work. And if you do Huron's formula, it would come out the same. All right, Huron's formula, remember, uses our sides, all right, by plugging into this equation. Do we remember what, or should we go through this one too, just to verify? Yeah. Okay, so S equals 1/2 A plus B plus C. And that's my sides. So that means 6 plus 8 plus 10 gives me 14, 24, 12. And then Huron's formula and it's very formulaic. And at least one thing that Huron's formula does do here is it verifies. Oh, look, by doing 1/2 base times height, I got 24 inches squared. By doing Huron's formula, I got 24 inches squared. Huron's formula is most useful when we don't have a right triangle and all you know are the sides and it's a scalene triangle. That's when it's most useful. Okay, back to, okay, so verified the area of the triangle 2 different ways, got the same answer, so we're definitely good there. Okay, and I have a semicircle diameter 10 inches. So a semicircle is 1/2 pi r squared. That is the area of a circle, and half of it is a semicircle. And then all I have to do is 1/2 pi times the radius. And what was the radius in this case? What are you doing? What is the radius of this one?
5.
5. Okay, we gotta let that catch up. And once again, then the shaded area is just the subtraction of the 2. Which then gives us 15-ish inches squared. All right, and one more. So I have a figure, right, which shows a circle, radius r with center at 0. Oh. Find the area of the shaded function as a function of this angle. Very similar to actually what we've done already. So I have 2 pieces here. I have a triangle and then a sector of a circle. So the area of the sector of the circle is 1/2 r squared theta. And actually, since that's theta, that equation is done. So actually, we found this piece. That is done. So then we're left with this triangle. Okay, we're told radius r. So it's radius r, angle theta. So actually I know that's r, and I know that is r. What is then this angle here?
-180 minus theta.
Ah, very good. Okay, because what we're about to do though, we're gonna go back to. So that angle is pi minus theta. All right, and that, because if that's theta, then it's pi minus theta, right? 180 degrees, pi, whatever you want to call it. Now, once again, notice what we have. We have side angle, side triangle. And we have our side angle, side area formula. So 1/2 O, A is R, B is R, sine of pi minus theta. Okay, so R times R times half is R squared over 2. Sine of pi minus theta. How do I deal with that? Does that look familiar at all? Someone familiar on the cheat sheet? Cat? It's kind of close, except cat is pi over 2. So but cat is a special case of what? We actually talked about cat as a special case of this formula we need to use. Okay, yeah, you can call it the same thing as me. They look familiar? Sum difference formulas. All right, the sum difference, they're bottom left. All right, it's these guys, right? So specifically, this one's pi minus theta, which means it's sine cosine plus, right? It's the opposite sign. Oh no, same sign. So sine cosine plus cosine sine. I don't want that whole thing in parentheses. And then we just have to do this piece at a time. So sine of pi is zero. Cosine of pi is negative, negative makes that sine of theta. And then actually simplifies down pretty nicely. This one is actually the opposite of what we have been doing. So in order to find the shaded region so far, we've done subtract, subtract. All right, I found the area of that shaded region, then I found the area of that shaded region. In this case, what mathematical operation do? We add them. And so, just so you don't feel like everything we've done so far is a waste, there is still stuff, all right, that we relate back to what we previously have done. And I could do that with numbers as well, but I wanted to show the relationship. All right, good stuff. All right, that is absolutely everything from chapter 7. We are going to look at chapter 8 next class, and then we have free day and quiz a week from Thursday. Yeah, but chapter 7 isn't too bad, right? No, it's not too bad at all. Good stuff. Back to the triangles. Bless.
Okay.